All right, quick video about light here. We talked a lot about this already in class. You can read these notes on your own. Did a couple demonstrations. We played with the laser a little bit. Now I'm gonna get into this and start going over this and reading this, do a couple of these calculations, get you going on this so then you can finish it in class. So refraction starts with first dealing with the speed of light. So wave speed moving through material depends upon the properties of the material. Behaves like a wave when it travels through space and interacts with objects. Speed of light in a vacuum is a constant we often use in physics. There it is. C is the constant, 3 times 10 to the 8th meters per second. Now, in any other medium other than air in a vacuum, light will slow down. So a material's ability to transmit light is something we call index of refraction. Air, oil, diamond, all these indexes of refraction. You can think of this as a multiplication factor, right? There's a simple way to calculate the index of refraction. If you know the speed of light in the air, divide it by the speed of light in the material. So this number tells you how many times faster light moves through air. So for instance, with a diamond, the index of refraction is 2.42. That means it's 2.42 times faster in air than it is in diamond, or it's 2.42 times slower in diamond. Because I could rearrange this equation. So your V, that's your speed in the material. Speed in the material. All right. So I multiply both sides. I cross multiply. C over N. This is the index, and this is the speed in air. So your speed in the material is the speed in air divided by the index. So speed of light moving through lucite would be, okay, the index of lucite is 1.5. So the speed in lucite, this is the speed of light in lucite, would be 3 times 10 to the 8th meters per second divided by 1.5. And there's no unit on index. So 3 divided by 1.5 is 2, right? 2 times 10 to the 8th meters per second is going to be your speed in air. Or in lucite, I'm sorry. I mentioned this in class quickly. So they've actually, in a lab, slowed a laser beam down to move at 17 meters per second. So what would the index of refraction have to be of that material? Well, N equals C over V. And I should show this as well. N equals C over V. So I multiply both sides. So V equals C over N. Right? That's how we plugged in there. So speed of light in air, 3 times 10 to the 8th meters per second. And speed of light in the material set is 17. So 3 over 17. So we do 3 times 10 to the 8th divided by 17 is 1.8 times 10 to the 7th. And notice the units cancel. So that's your index of refraction of that material. It's huge. It's very cool. But light still does travel through it. It's actually a quantum mechanical effect. So the speed of light is a constant in different materials, though it moves at different speeds. We kind of put it together with the wave equation, right? Speed of wave can always be determined by using the wave equation. V equals lambda F, or F lambda, right? So write the wave equation for light traveling through a vacuum. So in V equals C. So C equals lambda times frequency. Oops, lambda times frequency. Right, so we regularly have to convert between wavelength and frequency, and as long as we know the speed, we can do that. So determine the wavelength of a beam of light with the frequency of 6.3 times 10 to the Earth traveling through air. All right, so wavelength of a beam of light traveling through air, well, C is a constant, so C equals lambda F. We're looking for lambda, so lambda equals C over F. So So lambda would be 3 times 10 to the 8th meters per second divided by 6.3 times 10 to the 14th hertz. All right. That would be 3 times 10 to the 8th divided by 6.3 times 10 to the 14th. That will be 4.8 times 10 to the negative 7th meters, or 480 nanometers. Now, one thing I'd like to do here, it says determine the wavelength of a beam of light with the frequency of that traveling through quartz. Now, okay, so if it's traveling through quartz, what do we do here? How do we deal with this? Well, we would have to figure out the speed traveling through quartz and still use the wave equation, all right? So this is the thing. The frequency of light never changes, okay? It's the wavelength of the light that changes as it goes through different materials. The color of the light doesn't change, and I'll demonstrate this in class. So, let's go ahead and figure out the wavelength here. So V equals lambda F, all right? But V, we have to use N equals C over V to get it. So V equals C over N. Put that back in for V. So we get C over N equals lambda F. And we're looking for lambda, so we'll divide both sides by F. And we're going to get lambda equals C times F over N. Oops. Nope. My bad. C over N times F. So lambda equals 3 times 10 to the 8th meters per second. Quartz, I look it up on my table, index of refraction is 1.46 times the frequency, 5.1 times 10 to the 14th hertz. Okay, so plug that in. We've got 3 double E8 divided, oops. Trucking gas class is rocking over there. Friday afternoon, I suppose. I've got a wavelength of 4 times 10 to the negative 7th meters, or 400 nanometers. We often report wavelengths in nanometers. I'd like you to try number 6 using a reference table. You may have to find a reference table online, but you got to use the frequencies. So look up the color in the reference table. It's the electromagnetic spectrum, easy enough to find. See if you can figure that out. Speed changes, frequency remains constant. Answer that as well. Think about what we just talked about and try to answer that. We'll fill this in class. This one here we'll also do in class.